as you may remember from the first part, this proportional controller creates a certain offset, which is a not so nice thing with this sort of controller. Obviously, you can play around with this KP value, meaning with regards to the toilet water tank example, the lever, the ratio of the lever. So if you use another value there, you might be able to actually reduce that offset. Higher gain values, higher KP values decrease the offset, the steady state error. But if you choose too high values, that whole thing may become unstable. So there's a certain system-dependent limit of that value. Another concept of control is integral control. One final remark here. As mentioned, this equation, it considers the current error, the instantaneous error at this very point in time. Integral control considers the past error or the history of the error. The constitutive equation here is pretty similar to the proportional one. The only difference, though, is that we don't use the value of the error. We just integrate, meaning that we sum up all the errors over time. And by doing so, take into account the history of the error. And this actually, as we shall see in the next example, will enable us to get rid of this offset. Another type of control is derivative control. And again, we have some similar constitutive equation which relates the manipulated variable to, in this case, the derivative of the error, to the rate of change of the error, which means that you try to estimate the future of the error, sort of, right? The integral and the derivative control concepts, approaches, are not really used as a standalone sort of control. The integral might be, but the differential controller type, it's not a standalone control approach. So usually it is combined with the P control approach, as we have seen on in the first example. If we, for instance, combine this integral control type with the proportional control that we know, meaning that we put these two controlling concepts in parallel, and by doing so just basically combine the equations, we get this constitutive equation, which is the P part and the I part, the integral part. And this is actually reasonable with regards to the water toilet tank, because in order to get rid of the steady state error, which in this case shows the steady state situation, we have a certain offset here. Inflow equals outflow, right? So the rate of change of the water level in the tank is basically 0. The water level is steady, but it's not the initial value. There is an offset. By turning this knob here, you can manipulate the height of that floating ball with respect to the lever. Now, if you would be able to turn that knob in your water toilet tank, you could eventually move the floating ball, so to say, away from the water level. But I mean, the controller would act or react to that change, and you would actually be able to completely level out or get rid of this error by doing so. And this is nothing else but an integral controller action, which one could implement in this system additionally. Probably wouldn't make much sense for a water toilet tank, but nevertheless. Now, getting back to this function file, which we have used for the P controller, this here was the equation we solved for the P controller. The rate of change, which we have used. Now, if we add an I term to this equation, meaning if we add this integral and use again the very same concept that we take the derivative of the manipulated variable, which provides the rate of change of the error here, and the derivative of the integral is nothing but the error itself. Then we actually end up with this equation. We have this P proportional control term, the first one. And then we have the second part, the integral, which by taking the derivative we have sort of transferred to the error itself. So we have this integral constant here, Ki, and the error, which is the difference between the reference level, the height of the water tank at 0, and the current level. That's pretty much the only change in the controller. If we then rerun this example using an intermediate value for Kp, I think in this example here Kp is something in between 0.6. Then the integral part of the controller equation eventually gets rid of the error, as previously mentioned. We have the very same outflow profile again at 0.5 seconds. Someone presses the button, there's a certain outflow. And over time, this controller now, due to the integral, the additional integral control behavior, is actually able to get rid of this error. There is some dynamics here, right? It sort of slightly oscillates if we use a much longer time now with these numerical values. It would eventually level out at the reference level at 0.2. But here the outflow is set to 0 again after 15 seconds. So then we don't actually see this steady state behavior now. Another thing you can observe here is that we sort of exceed the boundaries of our little conceptual system model, because if we set the outflow to 0 at 15 seconds, this PI controller now is sort of so reactive that it sets the inflow rate negative in order to keep the level constant. And this is, I mean, very unphysical, obviously, but it's just a consequence of our very crude system. We haven't assigned any constraints to these valves that they, or to the flow rates, right? The main point here, though, is that by adding this integral behavior, in addition to the proportional, one may actually get rid of this steady state error. Again, just with the proportional, we can play around with the numerical values of this integral term constant ki, and by doing so, sort of tune the behavior of the controller. The larger these ki values are, the more responsive that thing is, the faster it reacts. But on the other hand, also these ki or these proportional integral controllers may become unstable if you set these values too high. I had a question in the break. I maybe did not point out this too precisely. In this equation here, the outflow is not constant because we, as I showed on the diagram or on the plot, it has a certain profile that we impose. It is 0 in the beginning. At 0.5 seconds, it's set to a certain value, and then at 15 seconds, it's set back to 0 again. So that means that this outflow in this equation basically changes in a discrete manner. And this equation here is not representing this profile, right? The only thing this equation does, it gives us a numerical reasonable or a physical reasonable numerical value for the outflow rate, which is, I don't know, something like 5 point something to the times 10 to the power of minus 4. That's pretty much what it does. So this is not the profile over time itself. It's just this numerical value there. Another concept that one could utilize is to combine this derivative control action with the proportional control action. The concept is pretty much the same as with the previous one. We use the proportional and the derivative control in parallel, which just results in a combination of these two equations into a single one. And by doing so, we don't only consider the current error with the proportional approach, we also take into account the rate of change of the error, meaning the way it may develop in the future. And this is something which you may need if you need a very fast response for systems which have large energy storages or which need to be controlled in a very precise and fast manner. Sorry. Getting back to our function file, okay. If you please ignore the highlighted term, the blue one. So everything which is black or light blue over white is the equation we want to take a look at now. This is the combination as it was just shown on the PowerPoint slide. We have this proportional term, and we have the derivative term. Again, we use this concept here. We take the derivative of the manipulated variable so that we can solve this equation over time. And if we do that, we will actually end up with a second order derivative for this for this term here, right? This is the derivative control action. It's the rate of change of the error. Since we are using the derivative of this equation in the function file, because we want to solve that over time, we will end up with the second derivative of the error. But we actually computing this already. We have that third equation here. The rate of change of that water level height. That's yet another differential equation that we solve. So we get basically the second derivative of the error. Okay. If we use that control approach, meaning proportional and derivative control, then we may actually speed up the controller response and yield a steady state offset faster than with the pure proportional control approach. We still, though, have to live with some sort of offset, right? Because in order to get rid of the offset, we need to make use of an integral approach. But by using a derivative concept in addition to the proportional control, we speed up the controller's response. Again, we can play around with the numerical values of that KD constant and yield different behaviors here. Now, as you might have guessed from the equation, which I use in the function file, oh, sorry, this is no good. There is a final goal where this all leads. It's basically the combination of all three different elements that we have seen so far. Proportional, integral, and derivative control in parallel, meaning that we combine all these three constitutive equations in one big equation. We have the manipulated variable as a consequence of the proportional control, of the integral control, second term, and of the derivative control type, third term. That's pretty much it. It's a combination of the three previous mentioned single element control types. And as just mentioned, or as previously mentioned, we, in order to use that in the function file in a more or less nice way, we take the derivative of this equation, and then we end up with the second equation, which again has three terms representing proportional, integral, and derivative control, but now with the respective derivative of the error variable in each term. This PID so-called PID controller, proportional integral derivative controller, is the standard workhorse in many technical systems, in many industries. So that's, I guess, what is used in most cases. And it is especially important when you have systems with large energy storage elements and you need a fast and high dynamic response of the controller, and due to the integral part, something with without a steady state error, right? Where you want to get rid of this steady state error totally. So it combines all the positive elements of the single controller types if you manage to tune it properly, meaning that you find reasonable numerical values for these three constants in the equation representing the PID controller, meaning Kp, Kd, and Ki. You may have seen that on the previous slides already. There is a different way to write this equation. You can basically exchange these Ki and Kd factors here using these expressions. The benefit of this is that this Kp then is valid for the whole equation, but it's just another way of writing it. But you may see these two different concepts in the literature, so you need to pay attention what form of the equation am I looking at. If you take some example from somewhere or some numerical values from somewhere, this is something to consider. Now, I was a little bit too fast with the last example. So the fourth subplot here is this PID controller, where we have all three terms as just mentioned in the controller equation. If we jump back to the function file, it's basically the whole equation now which is being considered for this fourth subplot. It's just a combination of all the previous ones. And by setting the numerical values of Kp, Ki, and Kd to 0, you can basically create any of the previous mentioned controllers, right? If you set Kd to 0, meaning the derivative term to 0, the result is just a PI, a proportional integral controller. So this PID controller is the most versatile, the most generic form, and you can basically generate all the others from this one. Now, in this example with the water toilet tank, this PID controller is not actually really doing anything better than, for instance, this PI. Because within the time frame and for the given numerical values, we reach some sort of steady state at a little bit more than 15 seconds in both cases. The only difference really is that this one here, where we have this additional derivative term, shows a little bit less oscillations, a little bit less controller dynamics, which may be beneficial in special applications, but as mentioned for this water toilet tank, it doesn't actually really matter. The problem with this, or not problem, but the task with any control strategy and any controller implementation is to find the best set of numerical values for these constants, Kd, Ki, and Kp. As you can see from this slide, the particular numerical values have a very large effect on the way the controller responds and the speed and the final value of the of the variable you want to control. There are certain ways to tune these PID regulators, or any controller which is based on P, I, and D concepts. And we will take a brief look into that in the next step. One, I guess, the most straightforward method to tune this PID controller, or any of the previously mentioned controller types, PI, PD controller, is to make use of the concept of Ziegler-Nichols, two guys who came up with this. And it's basically fairly straightforward. First of all, you record the system response by the system response that you get when you impose a step change on the system. So in our case, ignoring the controller, imposing a step change as we did, meaning pressing the flush button of the toilet water tank, will eventually just empty that water tank. So that the response here looks something like this. It's due to our very simple and crude model which we have used here. It's basically a linear change in water height over time, which is not correct physically, obviously, because this is highly nonlinear. If the height changes, the outflow will change in a nonlinear manner. But due to our crude model, this is what we have as a step response. And since the outflow is there and the inflow is not there, we have a decreasing value of water level height, right? Which is why our curve looks like this, and the curve given in this concept here looks vice versa. But that's just a matter of plus and minus assignment. Now, if we had modeled this one with additional elements, such as R elements accounting for the resistances, and especially an inertial element accounting for the inertia of the water mass, we would actually have ended up with some qualitative response like that. And then we could have used this tuning method right away, as it's mentioned here. But yeah, due to our crude system or system model, we cannot really use that one straightforwardly, because our system response does not show this behavior here. We basically neglect this behavior, which is a consequence of an additional energy storage element, such as an additional inertia that we don't have in our system. We just have one energy storage element, which is why our curve basically looks like this one, right? It's something like this and eventually levels out. Or maybe it doesn't even do that, because we have this simplification here. But nevertheless, in general, you measure the system response by imposing a step change to the system, as we did, meaning change the outflow, for instance, from 0 to something and then back to 0. So then you get a curve like this. And this curve can be interpreted in a special way. There are certain parameters which you can derive from this curve. And then, and this is the concept of these guys, Ziegler-Nichols, you use these empirical formulas to compute, let's say, fairly good values, numerical values for the PID or the PI or the P regulator. This is one way to obtain numerical values for these various controllers. There are other ways. I guess the most simplistic one is just experience. If you have dealt with a certain system and a certain controller for some years, you basically know the effect of the numerical values for your different controller terms in the equation, and don't really need anything like this, but this is a way of how you can actually derive it based on some concept. If you dive more into this topic and then also solve these equations in the frequency domain, there are more concepts which you can make use of to establish numerical values for your controller parameters, but this is out of scope for us here. If we take a look at Matlab, Matlab actually has quite some built-in functionalities. So there is, for instance, a function which is called Pid Tune, I think. Yes. Which helps you to basically tune the PID controller, assign certain numerical values for the individual constants in the equation. In order to do that, though, as far as I know at least, you have to use you have to solve all these equations in the frequency domain and not in the time domain. So it's not that straightforward for us. But the bottom line here is Matlab has some built-in functionalities to do that, and it's not that you really have to do that by hand if you ever need to. There is also another feature within Matlab. It's called Pid Tuner. I think it's based on this function actually, but it basically provides a graphical user interface to do this. Okay. And within this GUI, within this graphic user interface, you can basically tune a PID or any other regulator. You can, for instance, choose PID here, and then you need to import the response of the system as it was just shown on this PowerPoint slide, where the Ziegler-Nichols concept was briefly mentioned. It's a bit slow. Yes. So remember, we want the system's response to an imposed step. You can basically define the step here. I don't remember it precisely, but it's something like 5 to the power of 10 minus 4. The amplitude, meaning the water outflow rate. And then this happens after 0.5 seconds. So that's how our imposed step looks like. And here, you need to specify the response. which should be in our workspace as y. The last equation I solved here was the system response, this one. And this should be now available to this tuning functionality. Yep. I don't know if it... Yeah. So now you can basically tune the PID tuner to get the most nice or the best suited response, control response that you want to end up with. As an additional way, you may use this PID tuner function here within Matlab if you have to, for instance, for some exercises. Okay, so just to sum this up briefly, different types of controllers that you may use in order to control such a technical system. P and I can be used as standalone controllers, but in general, especially these days, a PID controller, I guess, is the standard workhorse in most applications. And the benefit of this one is that it basically combines all the benefits of the individual controllers, meaning that it has a very fast response. You get rid of the steady state error. And this is why it is being used in most cases. But if you don't have to, because the system's behavior over time is not that important, such as with this water tank, where you don't really care about the water level height as a user, a pure P control might actually be sufficient. So it pretty much depends on the particular case which controller to choose. And it also depends on the system that you want to control. If there are large storage elements in the system, meaning in our case, if the reservoir is large and if there's large inertia involved and the inflow and outflow rates are large, or the rate of changes are large, in order to prevent damage due to high flow rates and high pressures, you might have to use some control concept which has a very fast response, right? In order to not end up with pressure peaks, for instance. Okay, any questions? Then this has been it for today. Have a nice day.